All right. Well, hope everybody's having a good day. Good to see everybody. We are very close to the end of our first week back after vacation. It always seems like a long week, just getting back into the routine. Just kind of think about how it's going to be after Christmas, when we have 2 weeks off. But we'll get there eventually. Just a couple things. We should be able to finish up the lesson today. I've only got a couple of graphs left to show you. We'll practice graphing a few of those. And then tomorrow, I'm thinking we'll go ahead and take the class period. I'll probably give you the homework today, but tomorrow in class, we'll take the opportunity to just practice it. We won't move on with any new material. We'll just graph and graph and graph. I know it sounds sketchy, but it'll work out pretty nicely. See what I did there. Okay. And then next week, Friday the 7th, that's when your exam's going to be. So it is going to be over graphing trig functions, all 6 of them. In fact, the very first problem on there is going to be very similar to this quiz that we just took. Okay, same format. There's going to be a grid, a table, all that stuff. You'll fill in the information. Then I got some multiple choice questions in there, like maybe here's a function, what's the amplitude? Okay, what's the period? Things like that. And then at the end of it, I went ahead and put a couple of review questions for loft sines and cosines on there because, that's something we definitely want to remember as well. But that's coming up next Friday. Next week, we'll move on into inverses, and, we'll just see how far we're able to get before the end of the semester. All right, does anybody have any questions about what's going to be happening? All right. Well, Ms. Stern is going to pass back your papers, and while she does so, you'll notice the class average was a little low this time. That's okay. Not to say that a lot of people did bad on the quiz. A lot of people did really well. It's just that some other people did score a little lower. And let's go ahead and try to talk about what some of those misconceptions may have been. In fact, here's the quiz. -3 cosine of 1/2 x. Okay. Well, I want to go ahead and graph this guy. But first, let's go ahead and list all these items right here. So A is always in front. B is the coefficient of x. What's the value of C here? Yeah, 0. There is no value added or subtracted to x. And what's D? D is 0 as well. There is no vertical shift. Okay, so if I go ahead and start with the midline, that's always based on which one, A, B, C, or D? D. So since there is no vertical shift, it is 0, but there's something we always like to do. There you go. Lilibel is absolutely right. We want to write it as an equation. We always want to say y equals 0. Okay. Now my amplitude, remember that is the absolute value of A. Well, in this case, A is -3, so what's the absolute value? Yeah, it's just 3. Remember, that's half the height of your wave. Okay, does anybody remember what's the expression for the period? 2 pi over b. There we go. So the period is 2 pi over b. And in this case, b is equal to 1/2. Okay, so what happens when you divide by a fraction? Yeah. So this would be 2 pi times 2 over 1. So what we're going to get is 4 pi. So it should take 4 pi units before this graph repeats itself. In fact, you're only going to be able to see one period on this graph when you fill it in. Now, how do we find the frequency? There you go. It's just the reciprocal of the period. So the frequency is always b divided by 2 pi. So if I have 4 pi, then the frequency is just 1 over 4 pi. All I did was flip it. So that tells me I should see one cycle. It only repeats one time in a length of 4 pi. All right. And then now we have our critical points, but it actually says before the transformation. So what were the 5 critical points for cosine? Okay, so cosine always started at a maximum. Then a 0, -1, 0, maximum. Perfect. All right. Anybody have any questions on those? Okay. Well, now let's go ahead and turn our attention to filling in the table, and then I can go ahead and get some points here. Well, what do you want to start with, the x's or the y's? The y's, okay. Now, is there anything in that function that's going to change those 5 y values? Okay. Lilybell says the 3, and there's one other. That negative. Now, how do we know that would be vertical and not horizontal?
Because it's not in the parentheses.
There you go. It's outside the parentheses, so it has to apply to the critical. So each of these 5 I simply want to multiply by -3. Okay. So the first one, 1 times -3, -3. Then 0, +3, and then -3. Is everybody okay where I got those values? Okay. Now, let's go with the x's. Now, for the x's, we always have to create something that starts with a compound inequality. Now, if it's cosine or sine, you're always going to go between 0 and 2 pi. We'll talk about tangent and cotangent in just a second. But what's going to go in the middle here? There you go. Whatever's in the parentheses, whatever's happening horizontally, that's going to be put in right in the middle. Now, I want that to be x in the middle, not 1/2. So how do I take care of that? Okay. I'm going to multiply this expression by 2. So let's see. 2 times 0 is 0, less than or equal to, that'd be 2x over 2, so that's 1x, less than or equal to 4 pi. Okay. Yes. Now, before we get there, let's go ahead and match this up. The lower boundary, I got to be 0. I'm always going to pair it up with the first critical. The upper boundary, the 4 pi, I'm always going to pair him with the last critical. Now, this time we do know the distance between 0 and 4 pi is 4 pi, and Brandon's absolutely correct. Whatever that distance is, always divide by 4. So it looks like I'm going to be adding pi over and over again. So 0 plus pi, pi, plus pi, plus pi. And will 3 pi plus pi give me 4 pi? Yes, it should always match up. Now you'll notice some of these points aren't going to be on your grid, and that's okay, because you can use the pattern that you see to just fill in the rest. Like for example, we have 0, -3. So 0, and then I'm going to go down 3. Then we have pi 0, so I'm going to go right pi and then stay there. And then we have 2 pi 3. Okay, so 2 pi to the right, 3 up. Now let's kind of visualize this. The next one would be 3 pi and then 0. So visually kind of right about here, maybe a little outside the TV set. Is everybody okay with that? But see, you'll notice it already starts to repeat. So if I were to go back in the other direction, what would I have next? Would it be a 0 or a maximum? It would be a 0. Oh, okay. I guess I wasn't understanding the question.
I was seeing if I could shrink that graph because I was like,
Mhm.
they don't all fit there, and I was
Okay.
like, thanks, maybe I just messed up.
Yeah. No, you're good. And then now, what would the next one be? Would it be a minimum or a maximum? It'd be a maximum. There we go. And remember, what does cosine look like? It looks like a curvy what? V. So, oh, I drew that horribly. I can do better. Dang it. Let me try one more time, and no matter what happens this time, I'm going to do it. Yeah. There you go. So there you go. There's my curvy V. Okay. That would be -3 cosine of 1/2 x. There we go. Now remember, next week when it comes to your test, you're going to have to do another one of these. You'll fill out all this information, the table, the sketch, the graph, but it'll be tangent, cotangent, secant, or cosecant. Okay. Should be one of those. I believe I put one of those on the test. I'd have to check. Okay. But you do have to graph one of those. All right. Does anybody have any questions on the quiz? Okay. So if you are wanting to retake it, you have until next Thursday morning. You have a full week to come on in and talk to me about that. We did. Yeah, but it's one of those things that you got to be here to win type thing. Yeah. Sorry. I'll give you a high five if it makes you feel better. Okay. No high five for Mr. West? Oh, you want the high five? Okay, so remind me before I leave. I'll give you the high five. Yeah. Yeah, because you're going to leave at 12:36, right? Okay, well, you'll go to, there you go. Go talk to your friends about how awesome math was, you know. Okay. All right, let's go ahead and do a quick recap, and then we'll go ahead and get on with secant and cosecant. All right. So here's the thing. We've talked so far about sine, cosine, tangent, and cotangent. And we're graphing them the same way. We start with a compound inequality. We go ahead and take their critical values, and we change those if necessary. And then we just plot the points. Okay? Well, if you're trying to graph sine, or cosine, okay, your compound inequality, you're always going to put it between 0 and 2 pi, just like we did on this one every single time, right? Now, tangent and cotangent, remember, they were a little different. You had to use a consecutive pair of asymptotes. So if we want to sketch a graph of tangent, does anybody remember what those boundaries were? What were the asymptotes? What is it? Pi over 2. Okay, so pi over 2 was my upper boundary. Negative pi over 2 was my lower. And then again, what goes in the middle is what's in parentheses, the horizontal. Okay. Now for cotangent, okay, we're going to go ahead. Does anybody remember what the consecutive asymptotes were? 0 and pi. There you go. Okay. Now, we're already familiar with sine and cosine's critical values. Okay, we just saw cosines. Sine is 0, then a maximum 1, 0, negative 1, 0. But what were the 5 critical values for tangent? We started with an asymptote. Now, remember, we used no solution to show that. Then it went negative 1, 0, 1, then an asymptote. What was it for cotangent? 1, 0, negative 1. There we go. Okay. And then we just run through the process. Once you get your points, you sketch it, and you're good to go. Okay. So at this point, we're all caught up. The trig joke. It is hilarious. Thank you, Lily Bell. Okay. All right. Let's move on. Oh, lordy, lordy. Where am I? Okay, here we go. So here's secant and cosecant. So these are the notes we've been looking at for the past couple of days. All right. Now, I've already got all this information filled in for you. The only thing I really want to show you is how we get the graphs. Okay. And unless anybody wants to, I can tie it back to the unit circle, just like we've done with the others. But if you guys feel kind of confident, then I'll just show you the graph, and we'll go ahead and transform these. But if you do need an extra copy, they're right over there in the filing cabinet by Adolfo. Okay, just right over there. All right, so cosecant and secant. The cosecant and secant functions are reciprocal functions. What we're going to go ahead and do, if we ever want to go ahead and graph cosecant, we're first going to graph its reciprocal. Well, what's the reciprocal of cosecant? Sine. There we go. Okay, so we're going to go ahead and rewrite this. We're going to say 1 over sine of x, because that's the reciprocal. In fact, that's one of the identities that we're going to be looking at in a couple of weeks. Okay. Well, let's go ahead and do this. Let me give myself a little more room here. That's a parentheses. Or in fact, do you want me to kind of stop and give you a minute to copy before I start talking again? Okay, let me do that. Okay. Give you a chance to jot that information. Okay, so even though these graphs are going to look kind of peculiar, it's going to be pretty easy to graph them because you've actually already had practice at it, and we just haven't realized it yet. Okay, I'll show you what I mean in just a second. Okay, is everybody ready? Not quite yet? Okay. Just a quick check of vocabulary. Does anybody remember what we call transformation of a sine function? It's that unusual word. It starts with an S. Does anybody remember? If not, that's okay. You remember sinusoidal. Okay. Sounds like a dinosaur. There you go. Okay. Sinusoidal. But that just describes any function that has a transformation, in which, since we can relate it back to sine, we're going to say that it's a sinusoidal function. So both of these are going to be sinusoidal functions. So we have all this information here, but I'm just going to go ahead and focus more today on the actual graph. So let's go ahead and graph cosecant by graphing sine. Very similar to what we did with tangent and cotangent in the past few days. So we're going to draw this very lightly because we're going to be erasing sine. But where does sine start? Was he at a 0 or a maximum? He always started at a 0. So then we had a maximum, then a 0, then minimum, then a 0. And then we can continue this pattern in the other direction. So a minimum, 0, max, 0. Okay, so we're going to go ahead. There we go. We're going to graph him very lightly. Now, of course, mine I can't do lightly on here. It's just going to take the input. But here's the thing. I went ahead and wrote it like this because cosecant is going to have a problem everywhere that sine is what? Why would that be a problem for cosecant? Because it's reciprocal. What's the one thing we can't divide by? We can't divide by 0. So you remember when we did the same thing for tangent and cotangent? Wherever sine is 0, cosecant will have a what? An asymptote. So he crosses the x-axis here. There's a 0, an asymptote. 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 And asymptote. Okay. Now, that's only one part. We're not going to go ahead and erase sine just yet, because cosecant and secant, their periods consist of branches that open both upwards and downwards, and they look like parabolas. But they're not going to be parabolas. We're going to refer to those as branches. So everywhere sine has a maximum, we're going to draw what looks to be a parabola opening up. Well, here's another maximum, so I'm going to draw an upward opening one. But again, they're not parabolas the way we construct them. So we're going to call those branches. So what do you think is going to happen everywhere there's a minimum? There's going to be a downward opening one. Yes. So here's one opening down. Here's one opening down as well. Now I'm going to go back and erase my sine function. What I have left, that's cosecant. So like I said, he's a peculiar looking graph, okay? But this is going to continue forever in both directions. In fact, looking at the graph, can anybody tell me what's the period of cosecant? Okay. Oh, Lily Bell, you said it? What'd you say? 2 pi. See, it takes exactly 2 pi radians before it goes ahead and repeats again. So a period for cosecant consists of a branch opening up and opening down. Okay, so out of all of our trig functions, only 2 of them will have periods that are not 2 pi, that being tangent and cotangent. Cosecant and secant are going to have periods of 2 pi radians. And that makes sense because the reciprocal of cosecant is sine, and his period is 2 pi as well. All right. Now, let's go ahead and do the same thing for secant. Okay. In fact, the graphs are going to be very similar looking. It's just going to be shifted differently. So secant can be rewritten as 1 over cosine of x, because cosine is his reciprocal, right? So I'm going to start, in order to get the graph of secant, I'm going to start with cosine. Well, where does cosine begin? Maximum. So we have a maximum, 0, minimum, 0, maximum. And I'll go in the other direction. 0, minimum, 0, max. So we're going to draw this very lightly because we're going to erase him in just a second. Now it's the exact same idea. Secant is undefined when cosine is what? Wherever he's 0. You can't divide by 0. So just like the previous graph, wherever cosine touches the x-axis, Secant's going to have an asymptote. So I'm going to have an asymptote there, here, here, and here. Okay. Now I'm not going to go ahead and erase cosine just yet because I need the maximums and the minimums to know where those branches are going to be. Everywhere cosine has a maximum, I'm going to have what looks to be a parabola. It looks like it, but it's not. Okay, we're just going to call those branches. So I can have another one right here. I can have another one right here. And then on my graph, I'm showing two minimums where I'm going to have those branches opening down. Once I've got those asymptotes and the branches, now I can go back and erase cosine. And the result is going to be secant. I know what you're saying. Wait just a secant, Mr. West. How cool is that? Get it? Wait just a secant. Okay. Right, but is everybody okay how I got those two graphs? Okay. Again, what's the period of it? 2 pi. Okay, period for secant and cosecant is going to have both an upward and a downward opening branch. Okay, again, they look like parabolas, but we don't want to call them parabolas. Okay, because they're going to be bound by those asymptotes. Okay. Well, how are we going to go ahead and get these graphs if we want to transform them? They're super, super easy. Let me show you what I mean. Right at the bottom here, I've got two graphs. 2 cosecant of 1/2 x and -2 secant of 3x. Okay, we're going to get these graphs by graphing their reciprocal. Okay, so let's say this. 2 cosecant of 1/2 x. What's the reciprocal of cosecant? It's sine, right? So all I want to do is replace the trig function with the reciprocal. So 2 sine of x over 2. If I graph that, that graph is going to give me this one that I want. Okay. And see, here's what's really nice about this. Don't we already know how to graph sine and cosine? Yeah, that's what we've been practicing. Okay. In fact, what's the reciprocal of secant? Cosine. So if I'm going to graph him, I'm going to start by graphing his reciprocal. The only thing I'm going to change is the trig function itself. -2 cosine of 3x. Okay. So let me show you how this works. Forget about the 2 cosecant of 1/2 x. We're going to graph this guy. 2 sine of 1/2 x. And all the formulas are still the same. The amplitude is still the absolute value of a. The period is still going to be 2 pi over b. Okay. The midline, the vertical shift, is going to be taken care of by d. Okay. Everything we need. So let's see here. What would you like to start with? Do you want to start with the x values or the critical y values? Okay, let's start with the y values. Okay. What are the critical values for sine? Start at a 0, then a maximum. 0, and then a 0. Remember, those are the critical values for sine, right? So is there anything happening in this function that would change those? What is it? Yeah, see the 2 on the outside, we know he's vertical because he's not in what? He's not in the parentheses. So he has to affect these. So every one of these I simply want to multiply by 2. So 2 times 0, well, that's going to be easy on those. 2 times 1, and then 2 times -1. There we go, just like that. Okay. So I've got my y values of some ordered pairs. Okay. So now I'm going to remove those original because I have the ones I need. Now we're going to go ahead and set up a compound inequality. But if I'm graphing sine, what are my boundaries? 0 to 2 pi. So 0 less than or equal to, less than or equal to 2 pi. And see, we don't have to use any other boundaries for secant and cosecant because we're basing it off of the reciprocal. What do you think is going to go here in the middle? Yeah, whatever's in parentheses. So x over 2. Now I want x, not x over 2. Okay, let's multiply through by 2. So 2 times 0 is 0. Less than or equal to 2x over 2 is x. less than or equal to 4 pi. 2 times 2 pi. Is everybody with me so far? Okay. Oh, that was. The lower boundary is now going to pair with the first critical. So I'm going to put this 0 with this 0 here. Then the 4 pi, the upper boundary, goes with the last critical, just like we've always done. Okay. Now, how far is it from 0 to 4 pi? Okay. Well, it's 4 pi, right? And we always divide that distance by what? 4. So I'm going to be adding pi over and over again. So pi, 2 pi, 3 pi. Ooh, you think at Thanksgiving you got too much pie, right? Anyways. Okay. So is everybody okay with what I've done? Okay. Well, now we just plot these points. The first one being 0, 0. Okay, so that's the origin. Then we have pi 2. So I'm going to go pi to the right and then 2 up. Okay. Then we have 2 pi 0. Because remember, each of these columns here is an ordered pair. The x is on top, y below. So then we have 2 pi 0, 3 pi negative 2, and then we have 4 pi 0. Okay. Now let's also go ahead and fill this in going the other direction. Where would the next one be? It'd be a minimum. Okay. There we go. Okay. There you go. That's exactly right. Now, I'm going to go ahead and draw this graph, but I'm going to do so very lightly. So is everybody okay with what I've done? Okay. Now, here's the thing. This is great. I've got 2 sine of 1/2 x, but I didn't want that. I wanted 2 cosecant of 1/2 x. So how is this graph now going to help me get him? Well, how do I know where to put the asymptotes? Wherever this graph touches the x-axis, there's an asymptote. Well, how do I know where my branches are? Wherever there's a maximum and a minimum. So if there's a maximum, I'm going to draw the branch opening up. If there's a minimum, I'm going to draw it opening down. And then I'll go back and erase 2 sine of 1/2 x. There we go. That is the graph of 2 cosecant 1/2 x. Now, it's true, you can just go ahead and take the graph of the parent cosecant and apply the transformations and get the same thing, but actually I think it's way more efficient to go ahead and sketch it based off what you already know instead of doing something different. In fact, let's look at the period. What's the value of b? 1/2. Remember, it's always the coefficient of x, right? So 2 pi divided by 1/2, that would be 4 pi. And you'll notice it's both an upward and a downward opening branch that's going to be the period. And how far is my period on the graph? It is 4 pi. Okay. Does this make sense? Is there anybody who's not sure what I did? Anybody having trouble? Okay. Well, let's try the next one. Okay. Oh, I erased part of what I needed. We want to graph negative 2 cosine of 3x. Okay. The period will still be 2 pi over b. There we go. Okay. So I want to graph negative 2 cosine of 3x, which will easily give me the graph that I really want. So where should I start?
That's why I started putting a maximum, and then like doing the wood.
Oh, so you want to start by what's that, Brent? So you want to start with the criticals? that what you're talking about? Okay, those y values. What were the criticals for cosine? Remember, we started with a maximum, 0, minimum, 0 maximum. Okay. Now, what's happening here that I'm going to apply to these? The -2. Now, it's true, there's no parentheses around the 3x, but I know that has to be horizontal because the 3 and the x are connected directly. Okay, so I can throw parentheses around there if I wanted to. So the only thing outside is that -2. Well, -2 times 0 is still going to give me 0. -2 times 1? -2 times -1. And that would still be -2. So is everybody okay with how I changed my vertical transformations? Okay. So I'm going to go ahead and erase those. Okay, well, how do I get my x's going? Okay, so my compound inequality. Now, because I'm trying to graph cosine, I'm going to put that between what? Always 0 and 2 pi. But what's going to go in the middle here? The 3x. There we go. Okay. There you go. Now we want to simplify so we only have x in the middle. So this time I'm going to divide through. So I'm going to go ahead and take each part individually. So whatever I do to one part, I'm going to do to the others. 0 divided by 3? 0. Less than or equal to x, because those cancel. Less than or equal to 2 pi over 3. Okay. So 2/3 pi. And again, you'll notice, look at my grid. Is it set up nicely to help me with this? Yes. It has those values I need. Okay. So let's see here. How am I going to get these over with the y's? Okay, so the lower boundary, I always put with the first critical. Okay, so 2 pi over 3 would be right here. Okay. Is everybody with me? Now this one's easy. We started again at 0, so the distance from 0 to 2 pi over 3 is 2 pi over 3. But I want to always divide that distance by 4. Okay, so this is where it's going to get interesting. Remember, we're dividing by 4, so that would be the same as multiplying by what? 1/4. Because we can always take the reciprocal of what we have down here, because 4 is just 4 over 1, right? So we can say this is 2 pi over 3 times 1 over 4. So this is going to give me 2 pi over 12. And will that reduce it all? 1/6. So pi over 6. Okay. There we go. So that's what I want to add over and over again. Now, if you end up with an unusual fraction like this, I mean, that's okay. If you just want to count it out, then we can go back and simplify. Let me show you what I mean. What's 0 plus pi over 6? So you have 1 pi over 6. Plus pi over 6 would be 2 pi over 6, right? Plus another pi over 6 would be 3 pi over 6. Now, what would 3 pi over 6 plus another pi over 6 give me? It would be 4 pi over 6, right? But what would 4/6 become? See, it does become 2/3. Okay. So if it helps you, first off, to go ahead and write out the pattern, you know, absolutely. I can't do anything to pi over 6. What about 2 pi over 6? Yeah, that would be pi over 3. So I'll just go ahead and rewrite that. What about 3 pi over 6? Oh, pi over 2. There you go. Is everybody okay with that? Anybody have any questions? Okay. Well, let's see here. First ordered pair would be 0, -2. So 0, -2. Now you'll notice all of these are counting by 1/6. So this first one, that's 1/6 pi, 2/6 pi, 3/6 pi. There's the 4/6 pi. Okay, because that was the 2 pi over 3, right? So again, the graph is working with what you should be getting. All right. So let's see. So pi over 6, 0 would be right here. pi over 3, 2. Then we have pi over 2, 0. And then we have our 2 pi over 3, negative 2. Okay. Now that's going to represent part of your graph. Remember, we're trying to graph secant ultimately, but we're going with cosine now. So let's continue the pattern a couple of times. What would be the next one? Then it should be a 0. Then a max 0, min 0. And then just go in the other direction. 0, max, 0, min, 0, max, 0, min. Okay. There we go. All right, so that is the graph of negative 2 cosine of 3x. Would everybody agree? But I don't want that. I want negative 2 secant 3x. So how does this help me get it? Everywhere he touches the x-axis, you have an asymptote. This one actually has quite a few asymptotes, right? Now, how do I get the rest of the graph? Use the maxes and the mins. So every max, pretend it hit that, because I was off that point. There we go. We'll have a branch going up. Every min will have a branch going down. Now, when I go back and erase this guy right here, the result is going to be the graph that I wanted. There you go. Yes, sir. Actually, no, the period will still be found the same way, so it's no longer 2 pi. In fact, let's take a look at it. What's the value of b here? B is 3, right? So 2 pi over b, so the period should only be 2 pi over 3. So take a look, okay? It's only going to take 2/3 pi in order for this guy to repeat. All right, you can tell exactly what we got going on there. Does that make sense? Okay. In fact, just think about your transformations. We multiplied by 3, so the graph should have been horizontally shrunk, remember, because we take the reciprocal, if we were actually doing it by the transformations. So what do you guys think? Is it really difficult to graph secant and cosecant? No. If you do sine and cosine, man, you're golden. Okay. Good.